because it's the first time I think most of us have dealt with that type of program and language. So not even the interface is familiar. It's not like, I feel like Maya for us was much more easy to understand in the beginning than Unity.
Yeah, of course. Because Maya has like a much more intuitive UI. You don't need to worry about things. Like you can use things without truly understanding the computational background of them.
Okay. Yeah, I think there's like two things there. One is like, yeah, if you feel like it's moving too fast, or there's something you don't fundamentally understand, you shouldn't feel you should be okay to just stop Octavian and tell him, can you go over this specific concept, right? Like if you don't understand how a class works, if you don't understand how a for loop works, if you don't understand how a certain kind of variable, what's the difference between a float and an integer, all that kind of stuff, or a string, you should make sure that you ask those kind of questions, because that's the only way you learn these things. And Octavian and Alex won't be bothered by that kind of questions, right? That's why there's two of them on the tutorial, so they can help with everyone who has these kind of issues. If you're having concerns about things like the game of life, also you should feel fine to just stop Octavian and ask him about it, right? Like I don't fully understand the concept of the voxel. I don't understand how a voxel checks its neighbor. I don't understand the concept of the rule set. Any of that you should ask, because it's just super important for you guys to understand these fundamentals, because these are the fundamentals, right? The whole point of the Unity tutorials this term is that you pick up the basics of Unity through 2 or 3 things like particles and voxels, right? So the next thing the guys will be teaching you will be particles in Unity through the code platform. And obviously the benefit of all of this is that you guys are able to start to use this platform in your own studio projects next term and beyond, right? So it's really important that you get the fundamentals now, because we're not putting a lot of pressure on you to produce kind of studio work using Unity. The whole reason we're doing it like this now is so you pick up the fundamentals. So I'll talk Alex and Octavian, but also like for you guys, you don't feel worried to ask like, hey, I really don't understand what a for loop does, or I really don't understand how this if statement is working. And, just ask them to go through it time and time again. Like, we all expect it, to be honest. When I teach code, I know fully that people are going to, we're going to go 3 classes forward and they're like, oh, they didn't understand this thing we did in the first class. I have to go back, right? So we all expect that with this kind of stuff. It's very different than teaching Maya, where like Alex is saying, it's very intuitive and you can practice it much easier. And it's honestly like coding is like learning a new language, right? And it's very logic based, and there's no visual output immediately, right? So you don't get feedback that you're doing something right or wrong. So you just have to work with it a lot to get it. And again, we understand that not all of you will pick it up, but I think it'll be good that a good amount of you pick up the tool, so that there's enough of you per team who are able to use it meaningfully, right? And this is, I know, what Cheje also really cares about. And we don't want to see output immediately. We want to make sure that as soon as possible, you guys understand these coding platforms, because without that, the rest of the DRL gets very difficult, right? Because you don't have that ability in your team. So that's really important. And the second is like the behavior of Googling and finding YouTube tutorials. That's perfect, right? Like that's the kind of stuff we didn't have when we were learning this stuff, because there weren't Unity or C# or processing tutorials online very easily. And now you have tons of them. So, if you're doing your homework or rewatching a video and you forgot what a class is or an if statement, there's a lot of like good tutorials out there that will explain that stuff for you. And if that helps you, there's absolutely nothing wrong with it. Like honestly, coding is not easy, right? And learning it is never gonna feel easy. Like I think that's part of it as well, right? Like just accept that and try to enjoy the process of learning this, because it's a super useful tool for your future if you pick it up. And in a sense, we're giving you the space to learn that stuff now in the studio. So it's a great thing to have this term, to struggle with learning to code. So over the next few terms, the stuff gets much easier for you. But again, feel free to stop Octavian or Alex and ask them questions. And the classes are recorded, so you can keep following. If even like you and Alex have to pop out into a separate independent like Zoom room so he can explain something to a group of people while Octavian is moving forward, all of that is fine, because like the main session is being recorded. Right? This is the kind of stuff we couldn't do when we taught physically. It's one of the few advantages of Zoom. Right, so don't worry about doing stuff like that. And I know for a fact Octavian and Alex want you guys to be more vocal during the class, right? They want you to say, hey, I don't get this, or is this how this works? Because that's how they feel. They're getting feedback from you that you're learning, because otherwise they're just going to keep going, right? And assuming you're getting this stuff, right? So you need to speak up so that they know when to slow down, when to speed up, or when to show you something completely different.
I think in general, in my experience, silence equals lack of understanding, because when people don't ask anything, it either means that they've stopped following or they cannot follow. Not saying that it's their fault, it's just more of like a general attitude that I have seen in students. So it is good. Like if you don't understand something, feel free to interrupt. It's not a problem at all. You can also, if you don't want to interrupt the class, like vocally via muting, text me on Teams.
Yeah, or in the chat, whatever, however you guys are doing, it all works.
Yeah.
Yeah, I think that the problem was that Octavian thought that we already know these really fundamentals of coding, like what a loop is, what are all these. He thought that we already know all this. So we started struggling from the beginning. I mean, we couldn't really follow. We had to go back and then forth. So yes.
So you feel like there is maybe like a class of like a conceptual class on coding that is missing right now, that introduces concepts rather than how you actually do a for loop that does something inside of the unit or something like that.
Maybe we can start, like, if we can start following now, but I don't know. I'm not the appropriate person to talk about that. Maybe other people feel better.
Yes, but other people are quiet, so we're gonna have to go with you.
Yeah, I think in general, like, just like it would be beneficial for all of you if more of you kind of participate, speak up in the class. That stuff is really useful. Like it's your education, of course, so it's your choice to do what you want, and you guys are all adults, but like it's already a bit more difficult in Zoom. But like in the class, at least I could stop, or Alex could stop the whole class and just like make sure that some people were asking questions, but it's harder to do that in Zoom, especially with the whole camera issue and stuff. So like you just need really to speak up and ask questions. Otherwise, the tutors are not going to be able to understand what's happening with you. And yeah, I can't stress enough how useful it is for some parts of the team to pick up this platform, right? It's really important that some of you, at least one or two people per team, are able to use this platform moving forward if we're going to develop any kind of meaningful computational work in the studio. All right, how's it going otherwise? How was the rest of your week? Were you guys able to make progress as teams? You feel like you're getting into it now? It's like, what is it, the third week of the studio at this point? Yeah, I think it's definitely the third week. Okay, so I think the way we did it last week was pretty successful. If you guys, I'm assuming there's smaller PowerPoints this time than 100 slides per team. So if you want to go, let's start like that, and then we can see how you're developing, if you are in any way developing the digital work. Because if you're not, then maybe we can focus on that today a bit. So I think last time we started with team 1. Should we start with team 4 today?
I think we are team 4. We're the fire team. Okay. The host needs to enable.
Give me a second. Yeah, go for it.
Okay, I'm not going to go through the theoretical stuff again. This is like the diagram that we made after we talked last Saturday, just to start to categorize things a little bit better in our minds. So we started to try to find ways to simulate fire. In the beginning, we tried to do that through a simple 2D grid, the way we were working in the second workshop, just with an emitter, but that didn't seem very successful. So we began to explore fluids in Maya. We started with one emitter in a 2D container to try to illustrate smoke. And then we introduced a second emitter within the same container because we wanted to see how those two would mix into one and react with each other. And we also, we introduced a 3D object to illustrate the way that the two fluids would react with that through collision. And this is exactly the same, but it's just a matter of illustration with particles instead of this smoke looking like a fluid. And then we moved to a 3D container. This was like the most realistic attempt of us to sort of portray fire in Maya. Yunpeng?
So this is the parameters of the simulating fire, and the 3D container used to create fire and help us to understand what kind of parameters to affect the fire. And in processing of the generating the fire, so find some parameter to control the effect of fire. And this is about to use like different kinds of colors to simulate the radiation and to value them. Next. And this is, you mentioned that the gradient color, and we used the density emission map. And first we used the other software to have a map, to measure the temperature map. And we use this map to simulate, to construct a material, a gradient material to control with the fire. Here, simulate with the temperature, with the
Okay. Yeah, I think
Let me just.
what we talked about last week. Sorry.
No, I just went to the tile view.
Yeah. What we discussed last week was a concept of like, you're the fire team. It's heat. It's heat transfer. Through a medium. So I think like this is generally a decent start. I'm not too sure. The fluids will be the right direction for you guys. Unless we can do more with it than I know how to do with it. But like, I don't think it will be the right direction. But I think the kind of simulation of the transfer of energy through a kind of controlled network like the voxel network. So you guys are doing voxels with Octavian in the Game of Life. Slides 59, 60, and 61 is very similar, right? It's a grid neighborhood, in this case of 3D cubes, and you introduce information in one corner of that grid or anywhere in that grid, right? And you're looking for how that information moves throughout that grid, right? So I think the question is, okay, that is pretty simple, pretty intuitive concept, right? Like slide 61, when you're using Grasshopper to do that, that's basically what it is. You introduce a heat source, and then it shows you how the heat will move throughout that object, right? So I think what we should be doing now is getting a bit more diagrammatic about that diagram, right? So let's say if you started like on if you look at slide 59 in a simple 2D fashion, if you just had a grid of these cubes, we should start to use that as a simple diagram, right? So if you introduce heat in the center as an energy source, what does that mean, right? So in the case of the computation, let's say you change that cube from white to red, and you say that red is between 0 to 100%, right? So that cube is 100% red. And then in the next time step, you distribute the red to the neighbors around that cube, right? So that cube now goes from 100% to, let's say, 80%, because it's transferred to that 20% to its neighborhood. And that 20% is distributed in a certain way in its neighbors. And then that 20% in the next step gets transferred out. The 80% becomes 50% because it's continuing to transfer heat, right? So you're thinking about you're starting to think about this a bit more computationally diagrammatic, right? So how you're starting to understand how voxels work in code, right? Like you have the cube voxel, and it has the heat energy variable, which is 0 to 100. And then you have another variable called resistance, for example, or material resistance. And that variable goes between, let's say, 0 to 1 as well, right? So in a cube that has material resistance 1, all the energy that gets transferred into that cube gets transferred efficiently. You see what I mean? So if 20% energy is coming into that cube, it receives all 20%. But if that variable is 0.8, and you say energy absorbed equals heat multiplied by material resistance, so it becomes 20 multiplied by 0.8, you now get 17% of the energy coming, 17 instead of 20 coming in, right? And if it's 0.2, it's 0.2 times 20, you now get like you get 4 getting in, whatever, right? So you see what I mean? Like you're starting to think diagrammatically, but you're also starting to think diagrammatically about how the computation works, right? So that's what's really important. And then as you're doing this kind of diagram and these kind of models, we should also think about, what are the simple Grasshopper or Maya tools that we can use to kind of scale up the experiment while you are still working on your kind of Unity stuff, because ultimately we want to combine those two worlds. So yeah, like that's how I think we do the diagram experiment very easily. Like you can set up a simple grid population of voxels or cubes, and you say there's primarily 2 variables there to start. One is heat, one is material resistance, for example, and we can start to experiment with how heat is transferred through a population. And that's what we were talking about last time in terms of painting a mesh, perhaps, as a simulation for this. So I don't know, Alex, if you think that's still the right way based on what we're talking about today. How do we scale up this experimentation in Maya?
We could definitely do mesh painting. I also think that the fluids do have some hope for the project as well, but they cannot be used in the same way that we were using them in the class, because there's other methods in the fluids that can be explored. There's stuff like fuel and temperature within the fluid that can be visualized. So you can visualize kind of heat transfer and dissipation within a fluid container. So it's not so much about how the fluid just moves because of the emitter and the emission type. It's more about how the heat gets transferred inside of a fluid that might not be uniform, or it might be interacting with other objects. So exploring those properties and turning them on, because basically in the fluid, when you just create the container, these are not on. Like you only have, I think, velocity active, but fuel and temperature are also options that you can toggle, and you can shade based on them rather than on pressure or density.
We tried the fuel and temperature, but nothing happened.
Yeah, can you show us an example, Alex?
Just a sec. So I haven't personally worked with them. Can you stop sharing just for a second? And then
yes.
I'll take it. I haven't personally worked with them, so I'm not also fully sure how it would operate, but just minimize this. There we go. So in your content method, you have temperature and fuel, but they need to be turned on. So you should use a dynamic grid. And for example, right now, the differences between white and red are a consequence of the temperature, because in where's the shading? The shading method is using temperature to map a certain color. So this is showing a difference in temperature, essentially. Obviously, I made the mistake by making the red cold. You can make it blue if you want, but
I think this is what we did in the 3D container.
Yeah, I think you were using temperature to shade the incandescence, which is usually here.
Yes. Yeah.
Because that affects how the fluid is visualized. Like it looks, brighter. So like for a VFX artist, it might be relevant or important. Mm-hmm. But I think like if you just kind of start thinking about ways in which you can maybe affect or think about how this dissipation occurs or how it interacts with other objects, that might be a more useful use of the fuel component within the fluid object. So it's not even so much about, because you do have like a tab that relates to, where is it? Fuel temperature, which includes stuff like diffusion, dissipation, pressure threshold. All these variables do have, an effect on how, it develops as a.
My concern with fluid dynamics right now is like, for example, can you massively scale down the sampling grid of the fluid dynamics?
Yeah, I see what you mean. So,
like, what is that? 400? Do like 10.
Like they eventually, you're right, become a voxel grid. I mean, that's what they are computationally.
Can you visualize the grid?
I think so. I just need to turn it on. Just don't remember where it is. Display. Outline full. Yeah, this is it.
Okay, this is 2D, right, on y-axis, or is this a 3D? It's
2D.
Yeah.
It's just a emitter that is like a volume emitter, but it doesn't matter. It's only in the intersection with the 2D that actually.
Yeah, and can you visualize it as vectors instead of the color?
Yes, we can do velocity draw, but I think right now there is no velocity because I turned it off. So
Okay.
there should be something appearing. Yeah, there we go. It's just that like now it's forcing.
Okay, so you were just doing the heat piece instead of.
Yeah.
Okay, yeah, that's probably the right thing to do for this team.
Mm-hmm.
Okay, so can you switch off? Let's switch off the vectors, because we don't want to jump immediately to a very high scale population. Like, what I was explaining to you with the cube and the variable, you need to understand it at such a simple level, and that's why I'm asking if we can scale it down. So this is a simple omnidirectional linear fall off, basically, right?
Yeah.
And based on where you put that emitter. Is that an emitter, I guess?
Yes, this is the cube that I'm moving around is an emitter.
Yeah.
So obviously we can bound the amount of space that it has, and I think it should also probably affect this differently, because I think like in this situation that I just showed now, because it was close to the edge of the container, also it probably is reacting to that as well.
Can you make the emitter as big as the field?
Yeah.
And then let's see if we can play with other, because like the scale is a very weird parameter. It's just a Maya thing. Yeah. Okay, so if you press play now, it should spread to the whole field, right?
Yeah.
Yeah. So can we change the kind of energy available?
I think so.
In the emitter?
Definitely, there's stuff in the emitter itself that we can affect. So, where is it? Is it not showing? Come on. Oh, okay. There we go. So, like, the emitter attributes can be changed, but I think there should be other stuff. This is the density. Also has a heat method, so fuel method. So we can add more fuel or heat if we want to. We can also relate it to another object. I believe that these all accept maps. So if the emitter is actually a surface, and a surface has a map on it, like a shading map, it can.
But for example, can we just conceptually make this a cooler heat source, right? So the heat dissipation has a smaller fall off.
Yeah, it should be fine because we have dissipation as an option here. So right now it was max. Okay. So like the dissipation is greater, so there's more blue or smaller. Diffusion, I guess, was also.
Okay. But what we cannot do is edit per field the field attributes, or can we?
Like per voxel, you mean attributes?
Yeah, per voxel neighborhood.
I don't think so, because it always like outputs it as a global simulation. Like you could do it, I guess, if you just had a bunch of emitters, or.
Can you use a map to affect the fluid field?
You can definitely use a map to guide the emission. So like the emitter could be a surface, which is like 10 by 10, and each voxel within the surface can be different color, and that color can be something, like it can be, high heat, low heat, high fuel, low fuel. Like that's possible for sure.
Well, we can't edit the field parameters. Like this voxel is more resistant to dissipation, right? So
I see. No, I don't think so. It only works from the emitter to the field, not from field to emitter, or like field to itself.
Yeah. Okay. Yeah. So this could be a good diagrammatic start, but I think inherently for you guys, if you're not able to edit the field, that's going to be a problem down the line, right? Because we just know how this kind of computation works. As you move it to the code, what you're actually editing will be parameters in the field, as well as the kind of energy that you introduce into the field. You know what I mean? So that could be the fundamental limitation of this diagram. Although, like you could start to use it as a general diagram, right? Like introducing multi emitters or multiple heat sources,
You could use them as like a bitmap that becomes seeds, and if you bump up the resolution of the simulation, you could say like, oh, this is how heat transfer would work if in 3 points in this simulation there were a lot like very strong heat sources, and then they were dissipating slowly, and then you would get like a pattern out of it. So if you can maybe get some consequence from patterning to how it develops in the simulation, maybe that's like a semi-interesting strand of research that can be
And if you introduce a fuel, does that mean that after a certain period of time, the heat goes away? Is that what fuel does in the simulation?
I think fuel is just like the rate of change. So it should be like adding temperature and controlling the maximums. So it does give stuff like heat release, max temperature. I'm sure that these parameters are something that can be used to affect the rate of the change in the simulation.
Okay, but it seems like what you can affect very simply is the number of emitters, the dissipation rate of an emitter, the resolution of the parent grid.
This also seems quite interesting because I'm assuming ignition temperature is a sort of a trigger that occurs once a certain temperature is reached. So if temperatures from different emitters meet, they might have like an outcome that's quite interesting. Okay, so that's already changing.
Right, and at the end of the day, what you're trying to understand is how information moves through a field. Basically, like, we shouldn't lose sight of that, right? Like, this exercise is not about becoming accurate towards fire, right? What we're trying to say is we're abstracting the concept of fire into heat transfer. And what heat transfer is in a computational model is a transfer of information through a field, effectively, right? That field can be voxels, that field can be particles. But it's essentially the transfer of information through a field. And the core principle here is you have a field that's defined in a certain way. In what's on Alex's screen currently, it's a grid, right? And a voxel is just a 3-dimensional grid. And that field, even in how this is working in the back end of Maya, it will have a heat variable, right? So just like, can you guess what that heat variable will be stored at? What kind of variable? Like we were just talking about it. What do you think that variable is? What type of variable is it? Is it an integer, a float, a string? What do you think it is? Anyone can answer this. Does anyone have any idea how would you store the heat variable in a voxel? So how do you think you would numerically represent heat? Does anyone have any idea? Like, we were just talking about it, right? How would you store the information that is heat?
If it's from 0 to 1 or 0 to 100, then it should be an integer, no? Not the...
Well, yeah, if it's 0 to 100, it's an integer. If it's 0 to 1, you need it to be a float, right? To 0.3, right? So you just have a numerical integer that, or a numerical float that you have called, like, let's say float heat equals 0.0, right? And that means that voxel is cold. Float heat equals 1.0 means that voxel is hot. And what you're talking about then is you'll have a bunch of functions like void heat transfer that run every step of the simulation, right? Because then you're saying, how does heat transfer work? And heat transfer will be the transformation of that heat information between neighbors, right? The transfer of heat from somewhere else. It has to come from your neighbor, right? That voxel has to be touching another voxel for heat to be transferred to it, right? And the game is then, okay, how do you do what's called fall off, right? Like, which is what you're seeing on the screen now, which is how the heat expands, right? So you have things like linear fall off, you have things like radial fall offs. So I think as a team, you should even just Google this and try to do that work in your diagrams. What are the different forms of computational information transfer, right? And if you want to Google that, it's things like linear fall off, gradient fall off, radial fall off, all of these things, right? Linear fall off or linear interpolation is the simplest form of how this kind of transfer of information happens, right? You use it to simulate how color moves. You use it to simulate how things like heat moves. All of this stuff is called linear interpolation. It's a very important concept. So I really think you should take a look at it, right? So, but we should remember, like, all what we're talking about is how information moves in a population. In this case, the population is a population of voxels. So I think you guys can do a lot more interesting diagrams now, right? Like, you should have some really simple illustrator diagrams to illustrate this concept we just talked about. And then you can use things like Maya to do these larger scale simulations, to talk about what's possible through larger populations, through multiple emitters, by exploring different forms of dissipation. And then by, once we move back into Unity, you can start to explore things like the field parameters themselves, right? So parts of the population don't want to receive heat. Parts of the population want to receive heat, and that's just another piece of information, right? So can you think of two ways that you can influence a voxel in how it receives heat? Can anyone think of that?
To influence the voxel? I didn't hear the whole question.
Like, how do you think you would, using variables again, how would you influence a voxel to receive heat? How a voxel receives heat?
Maybe if you change the size of the voxel.
So size has no, like, in the simplest model we explained, right? So you have a function that tells you heat transfer, right? Which is, you look at your neighbor and you take a certain percentage of the heat from the neighbor. So, 1 second. Let's say, right? You have two cubes, right? And this one looks at this one. How will the heat transfer work between those two cubes?
Different colors. So
sorry?
different radiations and with different color temperature.
Okay, so what's the first thing you have to check, right? So let's say I want to transfer heat from here to here. How would you do that?
Difference in temperature?
Yeah, right. So first of all, you check each other's temperatures. That has to happen, right? Which means you have to have the float we talked about, which is float heat, right? So let's say there's float heat 0 to 1. This one looks at this one and says, am I colder than you or am I hotter than you, right? How do you do that in code? Does anyone have any idea? How would you check?
If
use the vector.
It's an if statement, right? It's I think Ola said that. It's an if statement, right? So you say, if my heat is less than your heat, then I'm colder than you, right? If my heat is higher than your heat, so you know the neighbor. So you say, if heat less than neighbor heat, right, then I'm colder. If heat is higher than neighbor heat, then I'm hotter, right? It's very simple. And based on that if statement, you either lose energy or gain energy, right? You see what I mean? So let's say the one on the left is hotter than the one on the right. That means this one gives energy to this one. And that's just a simple heat transfer function that you write called void heat transfer, let's say. And the inside of void heat transfer, the first thing you check is the if statement. So if I am colder than this one, I take heat. So if heat is less than neighbor heat, then neighbor heat minus 20%, heat plus 20%, right? So you have to lose energy somewhere to gain energy somewhere else. You can't just gain energy for free. If heat is higher than neighbor heat, then heat minus 20%, neighbor heat plus 20%, right? So if I'm hotter, I lose some energy and my neighbor gets it. If I'm cooler, my neighbor loses some energy and I get it, right? You see what I mean? And that's works really well when you just have two things in the population. But then you think about, okay, what happens when I have a grid? And I'm talking about the center one, right? The center one, it has to look at all its neighbors and say, okay, am I hotter than all my neighbors or am I colder than all my neighbors? That you have simple situations, right? If you're checking each one and saying, am I hotter than this one? Am I hotter than this one? And you're saying, okay, I know I'm colder than this one, so I'm going to get heat from it, but I'm hotter than this one now, so I'm giving it heat. So that's how you start to negotiate the transfer of heat in a population. Then the next step would be, okay, how much surface area do I share with my neighbor, right? So obviously, the central cube has more heat surface transfer with these four, right? Because it shares a face. With these four, it just shares a line. You see what I mean? Does that make sense? So with those, there's a higher ratio of heat transfer if I have a face-to-face connection, and there's a lower ratio of heat transfer if I only have an edge-to-edge connection, and there's no transfer of heat if you are one neighbor away from me, right? So you see what I mean? So you just check your immediate neighborhood, and maybe with these four, the heat transfer is in the neighborhood of 20%, and with these four, it's in the neighborhood of 10%, right? So that's how you start to get more intelligent simulations of how information moves through a field based on a simple concept like heat, right? And then the next thing we said is, let me just mix this up a bit. Depending on the color of the grid, you now have to also consider the color of the parent of the voxel, because that indicates a variable that says, float resistance, right? And if the resistance is 1, it takes no transfer. If the resistance is 0, it takes all of the transfer. If the resistance is half, it takes half of the transfer that was originally assigned. So by slowly adding this logic that manifests as a very simple set of if statements and functions, you create an intelligent model of information transfer in a grid, right? Based on the basic principles of how heat moves in the real world, right? So that's the idea of a computational simulation. We understand how the real world phenomenon works, and then we try to think about it as a diagram. So everything we just talked about is a diagram. And then we say, how do I turn that diagram into code? You see what I mean? And you basically, I know not a lot of you believe it, you have most of the tools already in the code to do that, right? It's just basically your ability to write if statements and variables and classes and check your neighbors, right? After that, that's most of what you need to do something like this, right? You write 3 or 4 functions, you go through the population, you can produce a basic simulation of heat transfer. And that's why I'm saying, look at things like linear interpolation, look at things like that, so you can see how that works and try to simulate it. And what Maya can do for you now is help you produce, like, on a small scale, make sure that the simulation makes sense before you scale it up, so that you can talk about what you're seeing there diagrammatically, and then we can try to simulate that in the code. Does that make sense? Right, and then when you move to the 3D, obviously it gets more complicated, because you now have 27 neighbors instead of 8 neighbors, right? So you just keep adding complexity to the simulation in various different ways. So that's what's really important for all teams, not just yours, which is what we're talking about is like the basic underlying computational principle being inspired by your elemental force, right? So your elemental force is heat. The basic thing we're talking about computationally is information transfer based on the concept of how heat moves in a medium, right? So does that help you guys, Team 4? Does that all make sense? Is that clearer today?
Yeah.
Who else is in Team 4?
I think it's clear.
Anayota speaking today. Who else is Team 4?
Yeah, I'm Team 4.
Yeah. Do you get what I'm talking about?
Yeah.
Okay.
Some a lot of difficulties about the data of the material value.
So
You mentioned that
what don't you understand?
I understand what you said, but
Okay.
yeah, I have some questions.
Yeah, ask them. It's fine. Like, that's why we're here.
Yeah, a lot of data value of materials, properties, how to put them, and combine them with our software.
Yeah. So
Yeah.
So okay, so you understood everything till the concept of materials, right? So
Yeah.
we're first operating without the idea of materials. So then, maybe a week from now, you want to introduce the idea of materials to this. We say, okay, what can a material do to the concept of heat transfer? It can either transfer heat better or worse, right? Essentially. So if it's wood, it's worse at transferring heat than metal, right? Do you agree with that?
Yeah.
Okay, so all we need to do is give that a variable in the code, right? For example, so let's choose a name. What should we call it? Conductivity, right? Heat conduction, right? It's how well the material conducts heat. So now this voxel previously had a variable which was its position, and it had a variable which was its heat, right? So there was float XYZ, which is its position, and it had float heat, which was its heat, right? And it had a function called heat transfer, which checked the neighborhood with a bunch of if statements. If I'm hotter, I give you heat. If I'm colder, I take heat from you, right? Now you want to add something else, which is conductivity, right? So you say one of the variables of the voxel, we're going to say is float conductivity, which is a variable between 0 and 1. And in your heat transfer function, you're saying, am I hotter than you? Okay, I'm going to give you heat. But now that I'm going to give you heat, I have to factor in your conductivity, right? So previously we said, if I'm hotter, my heat is minus 20%, your heat is plus 20%. Now you have to say, if I'm hotter, my heat is minus 20% multiplied by your conductivity value, and your heat is your heat multiplied by your conductivity, right? So 20% multiplied by 0.8 or 0.5. So if your conductivity is 0.5, I'm trying to give you 20%, but what ends up happening is I give you 10%, and the other 10% gets lost. You see what I mean? Or I keep that 10%, whatever you want to do. So that's how you start to introduce material principles. And if you run that simulation, what you'll start to see is the heat will move in the areas that are more conductive, and less heat will go into the areas that are less conductive, because they continue to take less energy every time the simulation runs. You see what I mean?
Yeah.
So, yeah, and again, all we've done there is we've changed how the information moves. So previously the information moved as it wanted. Now the information has to move with a consideration of another variable which simulates materiality, right?
Yeah.
Right. So, it's basically this kind of thing of like, how do you take a concept, diagram it, and convert it into computational logic, right? Yeah. So as you start to get more familiar with this stuff becomes very, very easy. But that's why this first step really matters for you guys to produce these diagrams.
Mm-hmm.
Okay, so I think for next week, what you should see is a whole bunch of like simple 2D Illustrator and Maya diagrams that show like just on a simple, 3x3 grid, the basic principle of how you think the information moves. And then you can start to use the Maya fluids that Alex was showing you or anything like that to do these larger scaled simulations.
Okay.
All right. All right. Thanks, guys.
Thank you.
Any other questions from Team Bor before we move on? Okay. Team 3, do you want to?
Yeah, we are Team 3, we are air group.
Okay. Do you want to share? Yeah.
This time we update some basic research. Next, please. One is about philosophy, the science, the performance of air pressure affects people's philosophy, like in hard or soft air shapes. Next, please. And we also do some research at the air environment control in two different ways, active or passive. Next, please. And we look at a company called Fastal Bionics. It has several robotic devices mimic various biology motions, and we think the main mechanism is the air inflation, which is maybe helpful for our project. Next, please. And this one is inspired by a fishtail fin. Next, please. This one is like a chameleon's tongue. And these are two examples of how air inflation devices can behave differently.
But can you get to your computational stuff? Did you do any computational studies?
Yeah, we can see the final. Like in page 92, I think. We just have a simulation strategy. Last time you told us we should simulate in Maya to do some air inflation, and so our thought is firstly simulating Maya's enclosed and particle, and to get some basic agency of behavior, and then try to use Unity to get to some more intelligent behavior, and then we will use Houdini to introduce the environment, like wind and temperature. But we haven't tried some simulation because we don't know how to use what kind of method, like
what kind of what, sorry?
What kind of method or shape to start simulate?
Yeah, so okay, just quickly, like, yeah, this is fine, but I don't think you need to go like these steps ahead, like Unity, and I don't know where Houdini came from, but so like what we talked about last time is a lot of your stuff was about things like air muscles, air inflation, controlling air as an inflation method, right? So we talked about using the Maya encloth simulation engine to do the basic behaviors of inflation, right? So again, very similar to the team before, we abstracted fire into heat and heat transfer, and what we just talked about. I think for you guys, what we talked about last time was this, the principle of air as an inflation mechanism and inflation as a model of actuation, right? Like a lot of your studies are essentially about how you use inflation to create motion, to create coordinated motion, like actuation, basically, right? So I think all of you would have used Maya encloth by now, right? Like the four of you. Yeah, workshop 1, the general tutorials with Alex last term outside of the workshop. So basically, you basically need to start, with the kind of simple inflation studies, right? So again, very similar to the team before you, the team 4, we're talking about what are the basic diagrams of the project. so that we can start to work on the more computational stuff, right? So the basic diagram of your project is inflation, right? So with the air project right now, your basic diagram is inflation. And then, how we move into different steps is, okay, now how do we start to do coordinated inflation, right? So for example, in workshop 1, all we did was we used to simply inflate the single piece of geometry, right? But you can think about more coordinated inflation in the sense, like, if you have, one simple principle is the idea of chambers, right? Like, you inflate this chamber, which then inflates these chambers, which then inflates these chambers, right? So a lot of your research is about this kind of chamber-based inflation, right? Like the Festo arm, all of this kind of stuff. You have to move air through something, right? So you just cannot inflate something all in the same time. There has to be a source of inflation which moves air throughout the geometry, right? So your simple diagram is like, let's say you have four geometries next to each other, right? Like 4 interconnected cubes. In the past, we would have just all inflated them in the same time, right? In the workshop, for example. But you can think about, okay, what happens if I inflate the left-hand side first, right? So first this one gets inflated, then this one, then this one, then this one, right? That's super simple. If you inflate the center, how does it work, right? Okay, I inflated this much, and then these two, and then these two. Also very simple. Okay, next thing, what if I only have a limited amount of inflation energy, right? So I don't have infinite. So what happens if I put all my inflation in the left? By the time it gets to the right, you're getting less and less energy, or less and less inflation. So you start to get a very different simulation than if you just were able to inflate all of them with the same amount of air, right? What happens if you start to introduce two areas of inflation, right? Same thing, again, what in Maya, it's very easy for you to explore this. Okay, now, next, if I start to color these meshes, and the color of my mesh affects the stretch resistance, which is all stuff we did in workshop 1, so I know you guys know how to do that. I'm introducing this concept of materiality, right? So maybe the corners are incredibly elastic, and the center is not elastic at all, right? So I'm going to get inflation on the ends and minor inflation in the center, right? For example. Yeah, go ahead.
Yeah, sorry, I just want to say that actually we didn't do some inflation simulation because we don't know if we can choose geometry, just to choose one geometry and to inflate it.
Yeah, I see what you mean. And don't worry about the geometry being like your physical project. The geometry is just a diagram now, right?
Just an agency, you mean?
It's just exactly. It's just a diagram. You can think of it like a circle. If you're doing in 2D, it doesn't matter, right? So it could be spheres, it could be cubes. It just needs the correct amount of subdivisions in Maya to allow you to do the inflation, right? So don't worry about how my project looks. We're trying to diagram the simple principles of inflation, right? So again, you have generic inflation. All of these inflate at the same time, right? And then you have the concept of chamber-based inflation, that you introduce inflation in one area of the geometry, and then it has to move to the other parts by switching on these other parts, right? And then you have, a limited amount of air, right? So you cannot put all the air you want into this. You have a limited amount of air. So how does that change the simulation? Then you can introduce concept of the material through mesh color, for example, right? You can start to introduce different types of particles inside the mesh that affect that as well, right? So you can do inflation using particles, not just simulation of encloth, but we can do that later, right? So there's many things we can explore, but you guys just need to start to generate the basic diagram. The next thing is like, how does inflation cause motion, right? So if you have something like this and you inflate it in the right way, it becomes like this, right? We're all very familiar with that, right? Yeah. And then you remove the air, it comes back like this, right? So that's like a lot of these Festo principles, which is actuation through inflation, And you can do that in Maya, because if you introduce air all in the same time, what will happen will just be like, right? It will go crazy. But if you introduce air like here, then here, then here, then here, you'll start to get this unfolding motion. And then you have to take it back in the same sequence to get the curling motion, right? So these are all the things you guys can explore as a kind of computational diagram of inflation, right? So there's basic inflation, there's chamber, or let's say sequence-based inflation. Then there's limited amount of air. So you start to affect the simulation by saying, okay, I can only put in whatever 50 air units instead of infinite. Then there's material influence. Then there is actuation as the goal, right? So what is the output? You want to move something. So I think the research is super clear for you guys. You just need to jump in and do it. And don't worry about the geometry and how it looks, right? It's just a diagram.
Yeah, besides, we didn't, after last class, we found that we didn't research the environment and wind and energy, so we have researched something about the harvest energy, and if we need to do some particle simulation to just use the wind energy and show how can they move in the environment or something like that.
Yeah, that's a very different kind of research, right?
Yeah.
So it's up to you if you want to do two kinds of things, right? One is like the inflation research, which I think you should do.
Yeah.
The other one is how an object operates inside a field, right? Which is, for example, like you guys looked at kites, right?
Yeah.
That's how a kite works. So you have a fluid dynamics field, for example, which is your air, but then you'll have to put an object inside the fluid dynamics. So what you care about is how the object moves inside the field, right? And again, you want to do it very, very simple. You start with a simple object where, let's say, if it's a 2D surface, is it in line with the field or is it perpendicular to the field, right? Which will change how much it moves. You're looking at the amount of force you're applying on it by affecting the parameters of the fluid, all this kind of stuff. So no matter what your research is, you have to do it this kind of very simple diagrammatic way so that you can build up the logic and explain it so that we can go back in the future and, like I'm saying, like with Team 4, talk about it in terms of variables and things like that. So I think for you guys, I think you should do your inflation studies. It's very, I think it's a very clear diagram. If you want to start thinking about this field, but I feel that would be very similar to what the water team does. But again, it's your choice.
Yeah, I understand.
Yeah, but I think it's important next time that you guys really, for the coming week, really focus on the computational work, right? You should continue this kind of research that you're doing. It's great. And it really helps us think through your project, but you also need the computational side, and like just get in touch with me and Alex if you need my help. And then Alex and Octave, just keep following the Unity tutorials for now. You don't need to use Unity for the studio yet. Yeah, it's just like.
Do you computationally know how to set up stuff that Mustafa was just talking about, like how you can plate the cloth in places, some places and not in others, how you can choreograph inflation rather than just inflating the cloth as a whole? No?
We can just try and...
No, I'm asking because I'm happy to show you. It's not about like you not knowing.
Yeah. Like we want to help you guys. You guys shouldn't feel like you want to ask us questions.
I'm not like trying to catch you out for not knowing how to do something in Maya.
Right. We want to help you guys so you guys can really take your research in a different direction, right? So we're more than happy to help you. So if this is really like for me, Alex and Octavian, just tell us if you don't know what we're talking about. We're more than happy. Like it's more frustrating if you don't say anything and then next week you don't do it, right? So it's much better that you just ask us now.
So I think like in general, the two possible options that you have is either separate the end cloths and animate them separately, like multiple objects, or we can use texture maps to control the amount of stretch resistance. So essentially, a high stretch resistance object will not inflate. So you can choreograph the switching in between inflation in that way as well. So
is that how you think is the best way to do sequence-based inflation?
I think so, because with the encloths, we can still keep them as separate ones and then just constrain them together. That's also an option. It's just that the results, in my experience, tend to be a bit messier. If you just kind of localize the amount of stretch resistance in different areas and animate that, I think the results tend to be a bit more controllable. They look nicer, essentially, but both are possible. It might be, you can try both and see what looks better, because maybe just having them as separate encloths may even work better for you.
So you're saying change the stretch resistance over time?
Yes.
To simulate sequenced inflation?
Yes. And
does that make sense to you guys?
Yeah.
Okay.
And I think it's even great, like if we at some point sort of include Unity into this, you can even play out a game of life as a bitmap and then load that up into Maya as a stretch resistance differential within your encloth object. So the animation of the game of life becomes something that drives inflation within the encloth object. Like that could be quite interesting, possibly. So you could have like a generative way to control how this sequencing of inflation is done. Whereas for now, while the Unity work is still a little bit early, you can do so by keyframing or like changing it on your own just to see the outcome.
What about using particles as the inflation force? Does that do good results in Maya? Like, I know you can have an encloth with a particle emitter inside it.
Yeah, that's definitely possible. It just tends to be computationally heavy.
Yeah,
like inflation in the encloth is much lighter. Okay. But yeah, we can also, because n objects like particles and cloths interact between each other. If you have a hollow encloth and put an emitter in it, you can absolutely fill it with.
Because that's the easiest way to introduce, at least conceptually, the easiest way to introduce inflation in one corner or one chamber, which then spreads to others. But I hear you, it's very computationally expensive. Yeah. So if one of you tries it, maybe you can try it as a concept, but with a very small amount of mesh resolution. So it moves faster. But basically what we're talking about is like, you know, like if you make a cube, an encloth, you can introduce inflation through the inflation parameter, right? But maybe Alex is going to show you. The other way you can do it is you put a particle emitter inside the cube, and the particles make the encloth inflate instead.
So definitely one of the options, like Mustafa was saying, is if we have, oops, why is my shader gone? Maybe if I rewind, assign new material. Oh, there we go. So if we have like a very basic encloth material, I'm just going to make a ball, right? And then in effects, we can just create an encloth from it. And then we can also create a particle emitter, which we can just move inside of this and make sure that our particle cloud has collisions and self-collisions on.
Switch off gravity.
Where's the nucleus? Goodbye. Like, well, maybe they're too small. Let me just see. Yeah, they're tiny. Let's make them a bit big. So particle size, let's say 0.5. These objects interact between each other because they're governed by the same solver. So you can see that this kind of is starting to stretch out your encloth just because it's filling up quite fast.
Yeah. Can you make the particle size maybe like 2?
Yeah. Where is it?
More aggressive.
That's a bit too much. Maybe 1.
Yeah, and we probably need to edit the encloth settings as well. So but it's definitely hard. This is definitely harder to do than just using the inflation.
Yeah. Okay, that was a bit better. It also depends on the terminal number of particles that you want to include. Like 70 seems to be already quite a high threshold for it at this size at least. So maybe we can just kill that on 60 or something like that.
Yes, but now you can think about it. If you have 2 spheres with a bridge in between them, but you only have the particles in one sphere, the particles will like fill up that sphere and then move to the next sphere, right? But that's why this makes sense for a lot of the sequence-based inflations. But we're very aware it's harder to control, right?
Yeah, and you will definitely have mixed results. But with that in mind, the other option is to control like the amount of stretch by introducing a different a different material property on top of the sphere. So, for example, I'll just do it again because mapping needs to be done beforehand. Let's just get rid of these. So if we have an enclosed object again, like this sphere, start an FX ray. So because we're using a map to drive the behavior, we need to map the object first. If you map it after you turn it to an enclosed, the map moves. It doesn't follow the transformation of the enclosed. It just moves within its own world space. So we want to attach it to the actual parts of the enclosed. So usually we just kind of apply a basic material. I will use a ramp map now. You can use whatever you like. It doesn't have to be this one. It can also be a file map that you introduce. I'll even leave it like this. It will just mean that these areas will inflate more and these will inflate less. So now that it's correctly placed on the object, you can just turn it into an enclosed.
I'm recording the session, by the way, so you guys can get this later.
Yeah, how would go?
So we go to dynamic properties. In the outliner, you can always turn off TAG objects only, and it will uncover all of the nodes within your scene, one of which will be the texture ramp or the file map, whichever you've chosen. And then in the dynamic properties maps, there might be something called like stretch resistance. You drop it there. And then usually, because you have to be careful with these colors, obviously zero, black is zero, and there's no such thing as like a zero stretch resistance fabric. It will just not do anything. So now I'm going to just change that to a bit more of a grayscale and then introduce some pressure. So maybe you cannot see it fully now, but there is more inflation in these sides that are darker. We can make that a bit more obvious by making them darker still. So like that. And you can also play with like the amount of difference that you have between them. So you see, like this creates like a more obvious change in between them.
Yeah, and what Alex is talking about is you keyframe this over time.
Yeah.
So you get a simulation of air transfer. You see what we mean?
Your UV coordinates are something that you can control, and now I have to play it first. So your UV position of your UV map can change, right? So it can go somewhere else, and that will be essentially what you use to control the amount of inflation. So when you rotate your frame, it goes there, and goes come back here. Like this is obviously more easily done on like map objects that already have like a planar map or something. But with all objects, which is quite nice, like when you model your low poly version in Maya, you can just select the object, go to the modeling tab, and you can explore this a little bit on your own as well. But there's the UV editor, which will allow you to unroll this surface. So essentially what you're seeing here is the concordance between the map and the part of the object which it is being applied to. So if I grab these faces that are in black, they actually correspond to what is black in the scene, right? So you can imagine that you can even create like a map that accommodates that each face has its own color. So you're only activating the sides of the cube with different colors. Mine right now is more random because it's just a ramp map, right? And you can also see that, when I change stuff within this one, it will change its position in the UV editor, right? So you can very easily imagine how this can be used. Like, oh, okay, so if I have 6 sides to one cube, I may be having a sequence in which like side 1, 2, and 3 expands a lot while the others don't, for example. You can also be a lot more complex as an object. You just start from an object that's low poly, because obviously if we are to make a new cube right now, it's so easy to change the mapping for this because you only are working with 6 faces. As you add more subdivisions, the faces will remain, or the mapping will remain in roughly the same position as you change the topology. And then it's much harder to change this if you need to adjust it to a new bitmap, but you've already done that in the low poly stage, so you don't have to do it again. So the idea is that your low poly objects will be the one that you will map correctly. And this is even a second step. First, just try to get comfortable with doing this with a map that's native to Maya. And then you can create a more complex object in which you can create like an object that bifurcates. It doesn't need to be just a sphere, you know, it can be something that has like some kind of typical layout, like radial or, you know, I don't know, circular or linear or branching or whatever. And then you can test out this technique on all of those separately. And of course, in addition to all of that, you also have the option to use constraints. So you could So you can even say like, okay, in your enclot, we can turn this into a component constraint, and that will keep the face together. But if the component constraint goes down in strength, it will actually allow it to expand. So essentially, maybe I chose a stupid part to constrain. I'll constrain the black part because that's the one that actually can change if the constraint changes. So I'm going to add a component constraint here. So imagine if I just reduce it. It gets to expand because its actual stretch resistance is low, but I can also use the component constraint to force it to go back down. And these are all just techniques by which you can do something quite easily, and you can keyframe it, right? Like this is just a value, just like the map is either white or black. It's really up to you how you want to use this. I think like depending on how you guys work, some people in your team might have better success with one technique than the other and so forth. But in any case, whichever approach you use, there is so much that you can do with enclot, and so many ways in which you can affect its control or like variability, because you can even use functions in order to control this strength. If you remember in the second workshop, one of the teams was using like a sine function to guide the position and the vector movement of one of their emitters. You can use the same function to affect the scalar value of the strength. So you can just like right click here and then create a new expression, and that expression will actually be what drives the change over time. So it like goes up and down, and then it's maybe in conjunction with some other constraint that is going up and down, but in a different place. So the amplitude of one is the value of the other. So there's many ways in which you can introduce control. Enclot is quite powerful and really nice with regards to that. So did that make sense?
Yeah.
Okay. I think you do have like quite a friendly computational model in your hands. So I think next week you should have a lot of tests that come about from this setup. Sharing.
All right. Thanks, guys. Should we move on to the next team?
Yeah. Thank you.
Team 2.
Hello, we are the next team, I think. I can share my screen. Yeah, so you know, we are the water team. We started looking at different ways of simulations and exploring our tools during this week. So first of all, what's happening? Sorry. We started looking at water as material from the previous week. So we have the phase changes, which is an important part of water as a material. And we decided to focus for this first set of simulations in water as liquid. So these are some different properties and behaviors of water. No, behaviors, not properties, which could be interesting to simulate and to look deeper on them. So yes. And these are special characteristics and properties that we could use as variables in our simulations. Looking at different setups in our simulation, we thought that we could experiment with an emitter and a container, an emitter and a collider object, an emitter and a container, a fluid emitter and a container, and we looked also at a smaller scale to bigger scale. So some thoughts about the different. We started exploring which are the possibilities that different softwares could provide. So we explored Maya and particle, fluid, and Bifrost for larger scales. And we started exploring also Houdini because we found out that it could be more powerful for larger scale particle populations. So when we have to deal with a larger scale particle population, it seems that it's a lot more powerful in simulation. And then how we could feed this data to Touch Designer. Yuji, you want to talk about the first set?
Then we moved from the droplets, from one droplet to several droplets, where we studied the stickiness of the water. When the stickiness is low on a smooth surface, it doesn't really stick on the object, but when it's high as 1 on a smooth surface or a smooth object, it sticks onto the object. And then we moved into looking into if the object itself, its surface is rough, will it still be sticky? And it's not really as sticky as on a smooth surface.
I think you skipped this.
I don't know why it doesn't go back. Okay. This one?
Yeah.
Yeah, this is an algorithmic simulation, I think, but we were thinking how we can do that in Maya, right?
Mm-hmm. Mhm.
This is like a test or an attempt to use the fluids in Maya. And we looked into the fluids that Alex had taught us like last term. And then one of the options that we had in Maya is the pond and ocean engine, or whatever they call it. And it's an attempt at what can we do with this as a field. The only thing that mattered in this is the density, like the density per second. This is the only thing that made this ripple effect. Other than other parameters didn't really do much change in that.
Mm-hmm.
So we moved to explore a little bit what Houdini gave us. So this is a set of simulation with larger populations, and we test different viscosity values. So obviously they diffuse more with lower viscosity, and they stick more to the object with higher viscosity. It might be interesting to just be able to study different shapes that are created from this collision. I don't know. Then we tested again the viscosity by pouring something into a container, let's say. Again, particles have a larger velocity towards the edges of the container and lower velocity as we move into the center of the container. This is by emitting again on an object. And here we can see also the velocity trails. But this is by tweaking surface tension. We see that it somehow breaks when we increase surface tension. They somehow tend to create groups. Particles tend to create groups, but break. They tend to break. I don't know how to explain that. Maybe. And this was an attempt again to pour, to emit fluid on a different, on a different geometry, like a sphere. So this is a bit laggy. Sorry for the quality, but it wasn't easy to render in its first phase. So yes, it could be again interesting to maybe study the patterns that are created according to different geometry and how the water gets shaped by the geometry on which is poured. I don't know. And as references, I don't know if we have to see this.
Mm-hmm. Okay.
This was more like references of how we could use some scripting in order to, I don't know, this shows how two liquids interact, for example. Yeah, and these are some touch designer explorations, but I don't think they're not relevant for now.
Okay, so which is really great. It's really good to see you guys kind of like dive into the material. So my basic question is like, what do you think is your diagram, right? Because I think that's an important question, especially for a team like you guys. What do you think is the basic diagram here? Right. So like, for example, with team 4, we talked about the heat transfer being an information, just a representation of how information flows. With team 3, we were talking about the basic diagram being, inflation and its attributes. What do you think is your core diagram in the research you've been trying? Mm-hmm. Kind of, right? They're actually computationally exactly the same. So there's not that much difference in their computation, which is why I'm asking, like, what do you think your diagram is? Like, let's say, what do you think the elements of your diagram are? Like, it's clearly particle based, right? That's one clear observation, right? Like your simulations are particle based simulations, right? And what's the other part? What's the other parts of these? What's the other elements of your diagram, do you think?
Like mainly there is a flow, like throughout our simulations, there is movement. But this is the issue that we're having. How can we diagram it? How are we supposed to, like, water is very, very, very adaptive, and like we're still like, we don't know how we diagram this.
No, we don't know. We thought that exactly, as Ola said, that maybe the most important property that we should highlight is how versatile the water is, how adaptive it is. I mean, find ways to work with this quality, probably.
Definitely one of the most interesting properties of water is phase changing, right?
Yeah.
Like, water has very different structures, like crystalline structures, gaseous and liquid structures that can be abstracted into an interaction between particles, because that's what it actually is, right? It's like different form of bond or link between water molecules in different phases that creates different physical properties. Thing is, like, I think that all of the tests, they show a lot of like breadth of research in terms of diving into computational models that you could potentially use, but I do think that some of them are too literal. Try to think of it in a more conceptual manner if we're talking about phase changing or changing the force essentially between the particles that's keeping them in place. Or I think even testing out stuff like in one of the simulations you were testing out incompressibility, or you were testing out stickiness and viscosity, like these can like an analog to differences in molecular interactions between molecules of water that could prove interesting for something that becomes a framework for an actual test and a catalog. I think, like, whereas maybe collision tests between like object and water, it's maybe too close. Like, I understand that Maya and Houdini pull you in that direction because that's what, as programs, they're supposed to do. Like, they're there for you to meaningfully simulate something that really looks like water, like they're a pond or an ocean or a water body of some sort. But I don't think that that is as interesting for you computationally. And I don't think it will necessarily result in a diagram that you can use in order to inform your work in Unity as well. I think actually the reference of phase changing based on temperature, meaning that the water reacts in its kind of on a molecular level to changes in environment, was actually quite interesting, because you could say that those interactions can become internal as well, so that the particles can decide how they relate to their neighbors based on a certain condition that is reached. So, maybe they will form stronger bonds or loose bonds, which is an analog or corresponds to water being gaseous, liquid, or crystalline. I think.
Yeah, I think, next week, Octavian will be teaching you guys with Alex flocking. And a lot of this will be a bit clearer, but essentially, I think your diagram is very, very simple, right? First and foremost, it's a particle diagram, and it's kind of what Alex is alluding to. It's a particle diagram that relates to the internal forces within the particles. So, more or less, we can call those the bonding forces, right? Because that is what a water simulation is in the way you guys are looking at it. So, I'm kind of glad you didn't necessarily go down the fluid dynamics route. You instead looked at water simulation as a body. So essentially what you have is two sets of forces, right? You have the bonding forces within the particles to create some sort of coherent body, right? Like whether that body is a water droplet, or whether that body is an ocean, right? So that's why I'm saying, yes, you're looking at various scales, but essentially the underlying diagram is essentially the same, with, of course, an immense amount of complexity to go from a droplet to an ocean. But it's essentially the same diagram, right? It's a population of particles held together by a certain amount of bonding forces, right? And, you'll see the first implementation of that in flocking with Octavian next week, right? Which is essentially a particle population held together by a certain amount of forces, except that in the flocking simulation, those are dynamic forces, right? So what keeps that coherence is the fact that these particles move together. In a water simulation, let's say, like, for example, a droplet, you have these internal bond forces, which are kind of like, we can think of them as a combination of attraction forces between particles combined with some radius-based collision, right? So those two things, like, these particles like to come towards each other, but when they get to a certain place, they don't go beyond, which is what intercompressivity, whatever that word is, intercompressivity, or I don't know why I can't say it, affects it, right? But it's essentially a collision radius combined with a collision amount or force combined with an attractive force, right? Those, you can think of that as your basic bonding diagrams, right? Two particles in their base state like to move towards each other because they have an attraction. So if they're within a certain distance of each other, they'll move towards each other. And once they're within a certain distance, they'll collide and not go any further, right? And if you make them, if they have a high bounciness, they bounce off of each other, right? But we know water doesn't have bounciness, right? So this is the basic diagram. And then you have a second set of forces, which are the forces that act on your particle body that affect their movement vectors, right? So a particle is a dot with a direction, right? We talked about this in workshop 2, right? It's a dot which has a vector which tells it which direction to move. And you'll see a lot of this again with Octavian and flocking. It becomes super crystal clear when you do that flocking diagram, right? But a lot of what you guys are talking about, like gravity or it being hit by a container or another particle body hitting it, these are just how other forces affect this internal body of particles, right? So, whether you produce this kind of digital material, like some of your foam studies and your water droplet studies, that's what you're kind of talking about. You're creating a digital material. And, Alex talks about like phase changing. You're basically changing things like the attractive forces, right? Like a gas has a much weaker attractive force than a solid, right? Does that make sense? Like ice, the attractive force is super strong, right? And it takes a lot of energy to break that attractive force, which is heat. And then gas has a super weak attractive force, right? That's why it disappears very quickly. Water is somewhere in between. So phase changing, which is this kind of abstract concept, computationally is just editing the attractive force. You see what I mean? Right? Mm-hmm. And so this is why, you don't have to be so concerned with the simulation phenomenon. What I mean by that is you're not trying to recreate a snowflake. You're not trying to recreate a simulation that gives you the exact accuracy of how fluid interact with complex geometries. That can come later. What you're hopefully never, but like what you're really trying to simulate is, or understand at this stage of the is logical diagrams of this phenomenon, right? Which is water. And you've chosen to look at water as a fluid, and you've chosen to look at that fluid as a particle body rather than a kind of CFD simulation, which is all about vectors and motion of the vector, right? You've chosen to look at it as a mass, which is the particle, right? Mm-hmm. So I think that's a good direction. I think you guys are very capable as a team. Obviously, you do a lot of interesting research, so that's completely fine. But what you don't want to get lost in is, don't forget that what we're exploring is the basic simulation. And the basic simulation is a particle simulation with a set of attractive forces and collisions based on radius. This is very easy to simulate in code, by the way. And
hi Mustafa. Definitely, can you show the last slide for the video a bit? Yeah, because in Touch Designer, I find it's quite interesting. It's kind of they can create the constant instant shape, and it can be stopped at real time. But in this case, I'm not so sure. I want to ask you or Alex if this can maybe actually export to the 3D software.
So I don't fully understand this or like Touch Designer, so I don't know how helpful I can be. But again, like this is probably just like some simple input of information. But that's what I'm saying. Like all of this can become useful down the line. What I want to have confidence in is, as a team, you guys understand your diagram, right? That's super important, because that diagram is so abstract. It can become anything, right? Like we were telling you 2 weeks ago, like maybe fluids don't matter 2 months from now, right? Yeah. But you started with this concept of fluids. We never know where you're going to go, but the basic computational diagram of the fluid body is super clear. And, you can explore things like phase changing. You can explore things like two bodies colliding. You can explore things like a body colliding with a rigid object. All that kind of stuff, if you understand the basic diagram. So I think like you've done a lot of good work. You need to now start this diagramming principle on this idea of a fluid body, right? So some of that foam stuff you were showing, I feel that's some of the simplest research you have at the moment, which is good. Like you can see like what I'm talking about here, right?
This is actually started from Sphere, and it's kind of combined with lots of particles. So with, like you said, about the radiation change and the force attraction and that kind of force applied, so it can actually create those constant form. But the thing is, I just wondering if in Touch Designer can also export to like 3D software.
Yeah, I don't know about Touch Designer, but like I think the basic diagram is super clear, right? And then we can talk about the kind of secondary forces that affect it, right? Like you can have the things like the attractive forces change across the population. You can have the introduction of an external force, like a massive change in the radius of part of the population affecting the overall population. But this diagram will start to tell us where we're going, right? Like, for example, like I'm saying, what you could be doing is building this digital material, right? And the question is then, okay, how do we then use this digital material? And does it bear any resemblance to water anymore? Does that even matter, et cetera, et cetera? Or we can start to think about how these particle bodies navigate other surfaces, right? So that's the kind of collision stuff you're showing in Houdini. But they all start from the same basic diagram of this interrelationship between particles being held together to create a fluid, essentially.
Yeah. Okay. Thanks.
Yeah, and in Maya, like even in this slide, incompressibility option is also something that you can cross-reference with viscosity. When you actually have your particle cloud, you can enable the liquid simulation, which I think you know, because otherwise you wouldn't have this property. And that is actually all of the properties there only relate to the relationships between the particles themselves. Like they're just attractive forces that allow them either to group or ungroup. Like you were saying that, you know, this can be a flat thing or a sphere. It just depends on the ability of the particle to push against its neighbors while also holding shape. So all of it is simply a force. And I think what was really good, especially in the last session when we had the research presented, I don't think that any of the teams really took these terminology of like fire, water, air, and earth too literal, which was great, because you could actually, when you take those concepts and you abstract them, you start thinking about them in a more applicable way. So it's not about like, oh, I want to make a simulation that kind of looks like water, so therefore it looks good because it's a good imitation of water. It's more about thinking about the background reasons of why water behaves in the way that it does, or why fire behaves in the way that it does, so that you can build an abstract, conceptual, and computing model that is, like most of us always saying, it's actually very simple. Like it's not something super complex. The complexity arises, you know, when you add other levels of interest and interaction between these elements.
Yeah, and I think, like I said, like, you know, when you guys go do the flocking exercise, it becomes a lot clearer. This one-to-one, it's very similar to the heat thing, but on particles, how these things interact, right? Because you still, if you think about it, particles have to check their neighbors, right? Because their behavior is based on neighbors, because an attractive force is just a force between you and your neighbor particles, right? So you're a particle, you have to look around you, see who your neighbors are, and then make an attractive force between your neighbors. Once you have an attractive force between your neighbors, they're going to come towards you. You have to check for collisions. Once you're able to control it to that level, you can start to make decisions like, okay, I'm going to treat different parts of my neighbors differently. And that's when it stops becoming water, right? Because water doesn't do that. Water, every particle is the same in the water, right? The only thing that you can change in water is stuff like temperature, for example. And again, if you think about what temperature is, it's just a variable of a particle, right? It's a float between 0 and 1. And again, the neighbor looks at another neighbor and says, are you hotter or colder? So it's exactly the heat team, but it's not operating in a voxel, it's operating in a particle. And what does heat do in your world? It vibrates a particle, for example, or it makes it more unstable, or it makes its attractive force weaker or stronger. And again, it's not about copying temperature exactly, although you could, because if you say there's a relationship between temperature and the attractive force, what you get is the phase change, right? Because the more heat you put in the body, the weaker it makes attraction than you get from a liquid to a gas, right? For example, if you take away temperature and you get stronger attractive forces, you get ice, right? So, and it's all, and what I'm saying is, what you can do in code that's hard to do in Maya is you can decide how to treat different neighbors in different ways based on their variables, because you're writing that code. And that's when it stops becoming a one-to-one simulation of liquids, because you're starting to introduce your own principles into the simulation, which then just says your computational inspiration was fluids, but this thing is no longer a fluid. You see what I mean? It's become a computational virtual material. You see how that works? Does that make sense?
Yeah.
Right. So that's the steps of this, and they all start from the dumbest possible diagram. Two particles find each other, they attract, they collide, they stop. You can change those basic two variables, how strongly they attract and how strongly they collide. And that's the basics of everything. You add more particles, all of that changes. and you can edit how you consider what is a neighbor. You can introduce motion. That's how this gets built up. And I think next week when we talk, you would have done the flocking. A lot of this will make more sense because you'll understand the concept of a particle neighborhood and making decisions based on the particle neighborhood. I think you guys understand the concept of a voxel neighborhood now because of Game of Life, and the concept of making a decision on a voxel neighborhood. It's exactly the same. You just tweak 2 or 3 different things to do it for particles, right? But I think that keep up this attitude. You guys are doing a good amount of work. You're being very free with your experimentation. That's great. I really like that. But don't lose sight of the diagram. Keep that very clear. Work on that because that will make the project much clearer. Okay. Any? Yes. Very little. Yeah, very little. It's just that you allow the particle to move in 3D. Or so, for example, in the things we were talking about, if it's a 2D simulation, its neighbors are only in 2D, and its vector is a 2D vector, right? So the particle can only move in 2 dimensions. So it's very similar to the voxel. If it's 2D, it only has a certain amount of neighbors. It only looks left and right. If it's 3D, it has to consider a sphere of neighbors. So obviously the simulation becomes more complex because it has more neighbors to interact with. So in terms of the principles of the interaction, there's no difference. You're just adding one more dimension, which adds more neighbors. And it also adds the ability for the particle to move in a different direction. You see what I mean? But the core principles are exactly the same. Particles collide, particles attract. It's exactly the same. Does that make sense? So it's very easy to take a 2D simulation into 3D and vice versa, because it's just like you're limiting the complexity or you're increasing it. There's not much more difference in that.
Can you tell me a little bit more about the Game of Life? I find it's quite interesting. And last time I had a chance in workshop, it's like more turned into coding with cellular automation.
Yeah, I think for you guys as a team right now in the studio, the Game of Life is less relevant. I think what you guys will do with flocking this week with Octavian, that will be a lot more relevant to you guys as a team. So, Game of Life, I don't think applies to this, but the flocking really does, right? It's much easier to translate the flocking model into a fluid model than the Game of Life.
Okay. Thanks.
Cute baby.
Doesn't matter, be a 2-dimensional diagram, but you can also be doing 3D. It really doesn't matter. It's the same. You'll see also you can do 2D flocking, you can do 3D flocking. It doesn't matter. It's exactly the same. It's just the logic is exactly the same. You just add one extra dimension.
I want to say
okay, thanks.
Yeah, I want to say we were also interested in phase changing, and I mean we true value in that wouldn't make a change. So the best way, as you said, is to look at phase changing in terms of coding only. We can't do anything in terms of regarding this.
Well, you can, because you now understand what you need to do, right? You can do in coding, you'll have a lot more control. But if you build a very simple particle body with a simple attractive set of forces, you won't exactly get ice or gas, but you'll be showing us your computational interpretation of phase, the attraction variable. And again, that's why you start with use all these ideas like phase changing based temperature, right? So that progression of information makes and of course, once you're coding, you can do it much better, because then you'll have to
molecules together, whereas with gas it's very loose. So like in particle simulation, you might turn on self-attractive forces and then vary them within the population between like the self-attraction being really strong and having a very big range to having a very small range, and then it becomes a loose material. I think like what I see for your project is actually kind of engineering, like Mustafa was saying, a material that really can phase change. Not sure if it's going to end up being like something that's water related, but it's definitely something that can...
It's a virtual material.
Exactly. You're thinking it as something that can change its internal structure, which has consequences for its behavior on a very high level, or how you experience it.
Yeah, and how it interacts with external force. And the only reason I say no springs is the problem with springs is it's very hard to reconfigure the internal infrastructure of the body, right? So once a particle is connected by a spring to another particle, it's forever connected. And we know that that's not how these things work, right? Yeah. They have an ability to break, they have an ability to move, and that's why a soft force, like an attractive force, is the right thing for you guys. So it's not like I'm fundamentally against springs. It's just, it's better for things like fabric than a fluid.
Yeah, sounds great.
Sorry. No. All right. Should we move on?
Yeah.
All right. Thanks, Team 2. All right, Team 1, Earth Team.
Yeah, let me share my screen.
Yep.
Yeah. Sorry.
Your screen is sharing that.
Let me quit screen share.
Okay, Team 1.
Okay. Could you see the screen?
Mm-hmm.
Yeah. This time we update our previous slide and update the catalog, which could start from the background and research. And sorry. We mainly focus on the concept of the transformation of energy, and so, as Theo suggested us last time, he said that we should focus on the concept of growth, then the biofabrication, and the difference between environment and genetics, and how the environment could affect it. So we do
the exploration on the rules of behavior and artificial life. So then we treat material as host environment. First is soil, and then atmosphere. Then it is the artificial environment, and then it's the vacuum, or we could say the outer space. And when we talk about the earth, when we talk about the soil, firstly, we see soil as a host environment for bacteria, and then bacteria has many growth forces such as multiply and self-replication, and the process of the simulation of the whole process could be in voxel and in particle. In voxel, we could use Unity, Game of Life, and then in particle, we could use Maya and Particles or and other engines. And when we talk about soil as host environment for plants, we look at, for example, the simulated growth of a tree. We could use AL system to simulate the growth, the process of the tree's growth, and then because of the mushroom could create bioelectricity, we could use bioelectricity as our energy supply to do further research or study. And the third one is soil as host environment for insects such as ants. And we focus on the ants colony algorithm with grasshopper plugging the Python to simulate the whole process. And this is the Game of Life. This is the AL system. This is the bioelectricity and mushroom, and then it is the ant colony algorithm with the grasshopper plugin. And then we focus on the material of atmosphere, because atmosphere could act as a host environment for birds. So in the Boyd simulation, we could say that when many birds, they are in the process of migration, they follow three basic rules, which are the separation, alignment, and cohesion. And we could use touch designer or other engines to simulate the whole process. And then we focus on the artificial environment because it could as a host environment for substance conversion, such as crystallization process. And we look at the Houdini simulation with the diffusion limited aggregation, which could be called DLA simulation. And we could use this engine to simulate this process. And then the outer space, we know that it is a vacuum environment, so it could as a host environment for plants and stars. So we could use grasshopper simulation of magnetic field to simulate the magnetization. And then outer space also could be like a host environment for space debris, just like Apple's project, the Space Oddity, which focus on the assemblage, the reconfiguration and transformation and movement. Yeah, this is our digital catalog, and then we also explore some case study, and we think Luca and Xiron could give us an introduction.
Yes. The first is that our system is about growth simulation and energy transform, and we mainly focus on the unite, how to transfer and simulate, and we divide it into two parts: the organic and the inorganic parts. For the organic parts, it's we divide it into the plants, the bacteria, the core, and the cell division. As for the plants growth behavior. It's like using the seeds and make it into the clay bricks. It will grow and convert from being a shelter to being a source of food. And it's a really traditional way. As for the second one, we use it. We do the bacteria growth stimulation. It has two ability. The one is about calcified, and the second is about its degradation. And the first one, it could do self-organize. It could, if we add some bacteria into the sand, it could do the self-organize into the sandstorm, and it shows the simulate of the diffusion behavior of sand as particles, and then put the bacteria into it to create the morphology that generated different sand forms. And create diverse forms of biofabrication. And the second one is about using mycelium, and it is a root system of mushrooms. As you can see, it has its own behavior, behavior pattern, and it can be used as a living glue to generate biomass and create unique forms. Also, it could do degradation and to create different forms and to create yes. So the third one is that we explore a computational approach. Please go down. Sorry. Yes. Just this one, the computational approach. Yes, we use it to do the biological it uses it to do the biological growth, that it creates something to wear, and add some bacteria in it to use the photosynthesis to create more things for human. And you can see, please go down. There is the growth of coral, and it can be controlled by the environment, like the sunlight, the fluid flow, and something else to influence its growth process. But also it will get influenced by the growth structure itself. And the last one is about cell division, and it's the basic mode of the growth. Like one create two, and the two create four. So.
So the another branch is inorganic substance, and we mainly focus on it in the landform. We can start in the sand. So firstly, about Free Otto, he focused on the physics of brown sand and desert dunes, and how the wind and outer environment influence sand pouring and dune formations. And you can see in this part, the Arena 3D printing group try to simulate sand behavior and the glue behavior. The group behavior, how to utilize it to influence the whole sand behavior. And in the fluvial landform, firstly, it focuses on how water under gravitation Coriolis force slope to enforce, transport, and accumulate on the Earth's surface. So this is a natural phenomenon, and how we can simulate it in the project. like this group, like the case, the swap. It started with simulation of the water erosion in different materials, like a sand clay mixture, and the water erosion in different conditions. Flow with ridges, like this picture, with different slopes, like the third photos. And another two landforms are similarized like the former one. The karst landform and the crystallization are quite similar. We can try to simulate the corrosion and the sedimentary of these materials. And we think this simulation can support the growth and or dismantle of our unit in the whole system. And the Xiaomen can good so in this and in this part is about the aggregation simulation. The first is like the fractal in 3D space, and the last is the L system.
So just quickly, guys,
Okay.
You guys are showing a ton of research, but and that's good. But again, same question I asked the other teams. What do you think your diagram is? What's the basic computational diagram here, right? So last time we talked about the Earth simulation, right? That, you know, we talked about Earth as potentially a material, Earth as a host material for something else. And I think you guys had a lot of that clarity in the beginning of this presentation. And then then you guys went into a lot of research stuff. So what did you actually do on the kind of computational model, computational diagram? So I understand everything as you guys talked about, but that's like 100 years from where you are now. So we need to take a step back and say like, okay, you have this very clear thing about Earth being a material, potentially a host material, if that's still the same argument, because, you know, this whole artificial life thing is very different, and that's a concept, it's not a computational diagram. So, you know, same question to like all the other three teams today. What is your computational diagram?
If you had to use one word to describe most of your concepts that you've introduced in this research, what would it be? Just one word.
Growth, maybe.
I would agree. Like for me, the interest seems to be in growth right now.
Yeah.
So as a computational model, what do you think that could mean? What could that look like, or how could that work if we're interested in growth?
Yes.
I think.
Okay, you go.
Okay, I think we could both use voxel and particle to simulate the whole process. Voxel is about the game of life. We could explore one cell and its neighbors, their relationship. And when in particle, we could use maybe the ant colony algorithm to simulate the behavior of an ant, or we could also use a L system to simulate the growth of a tree, and we could use the DLA simulation in Houdini to simulate the crystallization process.
No, I understand, but like your goal here is not to simulate every possible computational model, because DLA is a form of growth. You can argue the game of life is a form of growth. Ant colony is another one, but that's not the point, right? So the question is, you know, what is the diagram that you are using that will become the diagram of your project, right? So I think we agree that it's a you know, we went from the concept of Earth to potentially the concept of a growth model based on the idea of, you know, actually I think that link is not clear, right? Like how how you link growth back to Earth, I think is not clear right now. What we discussed last week is like the idea of Earth is like this host material, right? And it could be a so our another option, okay. If it is, then it's, you know, and then the question becomes, okay, you're trying to evaluate and copy. So with team 2, we talked about computation, right? It's the host model of water flow phenomenon they're trying to simulate, which an attraction or collision. Team and team 4, we talked about heat trap voxel environment. Back to you guys. Okay, growth in the voxel environment, for example. But what is the phenomenon we're trying to simulate, right? What are we trying to research? What are we trying to evaluate? And that's where things like, okay, we're going to talk about how two materials interact, right? That could be erosion, for example. Like I remember we talked about that last week. Or it could be a more growth model, like we're going to look at how by the introduction of a certain parameter, we start to evolve a growth system, right? So some of the research you guys were showing in the Miro landscape kind of growth models, which is based on a certain amount of cell subdivision to create growth, right? That's a very different model, right? That you subdivide and grow. That's a bit more complex. So basically, you guys have done a lot of great research. Your basic diagram is still very unclear, right? And that's the question we're asking.
Yeah, most of our, actually, we want to use bacteria working with soil, with skin, with plastic to explore the life cycle in the earth. And we want to simulate like bacterial degrading plastic or producing protein. But there's many algorithm in the growth simulation. We are not sure which one is suited for us, and what we can do in the simulation, not just the growth behavior. So this point is not clear. Okay.
So even if we start there, right, like the simulation you're looking at is bacterial growth on the Earth studies, right? And I think we talked about bacterial growth last week as well. We talked about bacterial growth in its host environment, right? So in the context of voxels, we talked about, okay, what is the basic concept of bacterial growth, right? And we talked about, okay, the basic concept of bacterial growth is cell subdivision, right? And cell subdivision is very simple. One voxel becomes two voxels, right? And then two voxels become 4, and then 4 voxels become 8. It's kind of exponential growth. So that's the most basic implementation of the idea of bacterial growth in a medium, right? And then it can go in various directions because you can talk a certain amount of resource available, right? Bacterial growth is still an energy-based process. In your case, the energy is quote unquote food, right? Or, resources that the bacteria uses to grow, which will influence the direction of growth. It will influence the amount of growth. And, in these kind of simulations, alive in the voxel, 10 units, you have to share that resource. And etc. And then you can also say some parts of the voxel network are friendly to the bacterial growth, while others are suitable for the bacterial growth. You can start to say that the bacterial growth has kind of object like goal-driven behavior, right? It's trying to go towards a certain direction or a certain resource, etc., etc., etc. But that all again starts from a very based on the exactly the game of life. You would have to do something like that. The Vox live or switching on again, right? In a voxel based, you have voxel reproduction because that's how bacteria grows. And you know, a lot of the studies you guys showed come from this kind of work, right? Some of the kind of growth models you've shown in the slide deck or on the mirror board come from that kind of growth. But it's a much higher, more complex thing. You can't just start from that model, right? That's like some of the stuff you have on the right that you were showing towards the end of the presentation. That's very complex stuff. You won't start by just doing that. And again, that's very different than DLA, right? Like diffusion limited aggregation is very different, right? It's just random growth, right? Like one particle moves and splits into two particles. Those particles move, split into two particles again, and it's very random. It has, you know, it's very hard to control diffusion limited aggregation, but it's essentially the same concept. It's a concept of motion and splitting, right? Which gives you the idea of growth. So again, you can simulate a lot of these basic principles inside either a particle network or a voxel network.
Yeah, I think actually, you know, simulating growth in Maya with particles is incredibly easy. I think like a lot of the output in the second workshop from the team that dealt with growth demonstrated how easy it was. The growth is of an interest is to you know, like what is for you, what around, does it mean that there's a source of food, environmental effect or soil that organic material then becomes something that's that as fuel to grow, that you can try to answer. Start off very simple, like, you know, a container of other particles that are type, it can eat it and kind of sustenance. These are all interesting questions that you can try to answer in your computation particle in a container of other particles that are considered to be food or soil, if you like. Once it hits a particle, gets a certain size, the size reaches a certain terminal size they can do as a single-celled organism. Mitosis occurs and they are able to split. Then they can.
Point one, you switch off the voxel. On the voxel. Really easy. It's dead if it doesn't. Try to introduce energy to the network. now. You just give energy to one particle or one voxel to start. And if there's enough energy for that voxel, it splits, right? So if it's above 0.5, it splits and it gives energy to its two daughter cells, right? So two new voxels are created and they take half the energy of the parent voxel. So now the parent voxel has 0.25 energy left, and the first daughter voxel has 0.125, and the other one has 0.125, right? So they have just enough energy to survive, but they don't have enough energy to grow, right? So that will be a basically fairly simple simulation, because one voxel becomes two more, so there's 3 total voxels, and that's it, end of simulation, right? Unless you add voxels started with 10 energy instead of just 0.5, then the simulation keeps going, right? Because there's enough resources for more and more bacterial growth. And then, you can start to do things like adding a random factor to the voxel to say, if who gets more energy? Do the two cells get equal amount of energy, or do you randomly say this child will get more than this child, and then you'll start to get differentiated growth, right? Because without that, you'll just get symmetric growth, right? This one will become this one, these two will become these two, and it just symmetrically grows. But if you add a random factor or something else like some decision-making factor, which we can talk about later, you start to get growth more in one direction, or growth more based on one child than another child because that child is stronger. So again, a very simple concept of digital diagram with a very clear set of rules that can grow the model and get you to the level of complexity you're looking at. And whether that's artificial life or whether that's an artificial medium or material, it doesn't matter. But again, if you want to call it artificial life, that's fine. And so we can look at a set of voxels as a single thing that has a certain amount of energy that allows it to grow, allows it to do certain things, etc., etc., etc. Right? So that's the basic concept, right? Which is using energy to grow or using energy to stay alive. And that's how you represent it in a computational model. Does that make sense?
Yeah.
I have a question. Sorry. I don't know whether my understanding of the voxel is right. I think, do you mean voxel is a kind of grid, such as Game of Life or Cellular Automata? Because it has
the voxel is the basic square in the grid, right? That's all we're talking about. Game of Life and Cellular Automata are just the rules that apply to that network. A voxel is just a single cube in that grid, right? So, but what they share is the concept of the cube, where you give the cube some parameters, or the single unit, and the fact that the neighborhood of it is pretty clear, right? That it has those 8 neighbors. So when you're creating your children growth cells, it will have to be in the neighborhood of that cell, right?
Yeah, and from my perspective, the difference between voxel and particle, I think maybe the particle is more complex or free. I don't know how to differentiate the two ideas.
It's not that particles are more complex or anything like that. They just have one is not constrained to a grid and the other one is, right?
Yeah.
But if you guys are going to do a growth model, I would heavily recommend that you stick to voxels, because growth in particles is very hard to control. It's very unconstrained, and it has very, we've just seen it a lot before, and we know what are the issues with it. So if you're exploring a growth model, I would really recommend you start in the voxel environment.
Particles tend to have so much more of their own internal character with regards to movement that it makes the resultant growth model look a bit messy. Whereas a voxel is part of a static grid, so you kind of are more in control of what happens when the model is output. Like it's not basically simulation is not muddied by other external physics that are occurring within the particle system.
For example, the Boyce simulation is a kind of particle or voxel. I think. But
the flocking is 100% particle based, right? That's agent based.
Yeah.
But that's not a growth.
Mm-hmm.
And we